Hey, full nerd fans! I'm here at Intel's Tech Tour with Rajshree Chabukswar, who is the software architect at Intel.
Yes.
I guess there's a bunch of software architects. But we're going to talk about Thread Director, and I think it would be really useful to kind of start with a high-level overview
Absolutely.
of what Thread Director does, how it works with the different operating systems, and kind of what we mean when we talk about Thread Director.
Absolutely, yeah. Happy to be here. Nice to meet you all. So, since we introduced hybrid architecture, which is in Alder Lake timeframe, we knew that we have two different microarchitectures, right? You saw Steven's talk yesterday. We have different buffer sizes, queue sizes, resources, cache. So even though we support same instruction set, it is different in terms of the performance or IPC it provides. So when the concept of hybrid came along, the first question that came to us is, how do we guide operating system to make sure that the right work lands on right course? Because when we look at Alder Lake, I don't know if you guys have looked at it, but in terms of like VNNI throughput, we had bigger performance delta between P and E core in Alder Lake. Now that has gone down significantly, but when we started, it was bigger. So let's say somebody is doing CPU-based AI, which is VNNI, and somebody is doing some generic work, which is scalar operations. And you have two cores available, one P core and one E core. Which work should operating system schedule on P core versus E core? Operating system doesn't know, ISA differences, IPC differences, and that's where Thread Director comes in, and it tells that, hey, I'm running class 2, which is VNNI work, right? Prioritize it for P cores.
Okay, so we have essentially big cores are P cores and little cores and E cores, and the OS is deciding where all this stuff goes naturally, because that's the way it's always worked before.
Absolutely.
But now the OS isn't necessarily aware what the strengths and weaknesses of the different cores are, and does it have a good idea of the rest of the state of the system, like what's going on with the GPU and what's going on with RAM and other stuff like that as well?
Yeah, so operating system for GPU side, they have their DirectX kernel, right? They send the work there, and things happen on the GPU side as they submit the work there, etc. But on the core side, the scheduler that we are talking about here is basically the core scheduler.
Okay.
So that one is where the Thread Director comes in and says that, hey, the big core, the P core that I have, I want to prioritize certain things, certain type of threads or instructions on them versus E core that I have, and I want to prioritize something else for that, right? And that's where the Thread Director comes.
Oh, wow, okay. And then the other thing that I didn't really understand until we were talking the other day, or yesterday, is that neither side has complete information, right? The Thread Director doesn't know what's going on in the OS side necessarily, and the OS doesn't necessarily know everything about the CPU. So how do you kind of reconcile that?
Oh, that's a great question. So OS, for example, has awareness into what's the priority of the thread, right? Then we have quality of service, which means that if something is background, they run it at low quality of service. Something is foreground, it's high quality of service, right? User initiated task. Developers can use APIs to say, I'm not high priority even though I'm foreground. And those are called eco quality of service.
So something like a Teams window that's always running in the background is a low priority
Absolutely.
service. Okay.
Yeah. And then, so some of these things, we don't have awareness of that in hardware, right? In hardware, we have awareness of what instructions are running, what is the performance delta or IPC delta, what's the power budget for my CPU versus other IPs that I have, am I running into some power thermal constraints, etc., right? So what we do is combine what we know and make it available to OS as a hint. And then OS uses its own goodness plus this information to come up with scheduling decisions.
Okay, so we've seen over the last few years since Alder Lake came out, we've seen a pretty dramatic increase in the I don't want to say performance because that's not exactly right, but it seems like you're doing a much better job of getting the right threads on the right cores at the right time. And I'm curious, how far on that path do you think we are right now? If we're on a scale of 1 to 10, and 1 is the least optimized, and 10 is perfectly optimized where every thread lands on exactly the right core at exactly the right moment for this state of the machine, where are we on Windows right now?
We are pretty close to, I wouldn't say full 10, but we are pretty close to that because what happens is when we provide a hint to operating system, at least Windows side of things, right? Linux is, at different stages on where they are at on using some of this feedback, but at least on Windows side, they consume this feedback. We have kind of co-architected interfaces with them, and every time we have new generation coming out, such as Panther Lake, we work with them ahead of time to make sure that if there are any changes that are coming to the interfaces, if there is any information changes that are coming in, we expose it to them ahead of time, right? So it's really a co-design effort.
And then they do updates to the OS, you do updates to the architecture, and hopefully everything comes in at exactly the same time.
Absolutely, yeah. And before even we productize it, like in Alder Lake and things, we had emulators with Microsoft, basically saying that, hey, we don't have hardware yet, but this is the feedback you are going to get. Let's figure out how the operating system consumes it, come up with scheduling. So there's a lot of engineering work goes together working with Microsoft on this front. So we improve every generation. Is it perfect 10? Probably not yet, and we have more things to work on, but it's fairly close to that.
And it seems like it's a really complicated computer science topic that maybe there is no ultimate perfect solution.
Absolutely.
We do the best we can.
I mean, if you look at it, the use cases are evolving as we speak, right? People come up with, hey, I want to run this AI in parallel. There's Copilot. There is, 100 windows open. People are doing different things. And that's where we do our evolution in Threat Director. I talked about yesterday where, our training of all these internal models for classification and everything consumes real world use cases. We keep expanding on that every generation because we know that the usage is changing as we speak.
So that's another interesting thing that I didn't really fully understand before. When you say you're training based on this, it's not like you have a list of executables and you know that Discord always goes on an E-core and Quake always goes on a P-core. You're looking at the behavior of the...
Absolutely, absolutely. So there is no static listing of anything that, hey, Teams is this, Edge is this, Chrome is this or anything, right? It is load on the CPU and the instruction sets that they are executing. Based on that, we do classification. Now, if something is low quality of service and OS sees that, hey, I see this is class 2, but it's low priority, I'm not going to prioritize it to P cores because OS figures out that by themselves after consuming our information, right?
Okay.
So that's where kind of there's no static listing, there's no binary identification of anything of that sort.
So then how does this all interact with the Windows, with that slider in Windows? It's like best battery, balanced performance, high performance.
That's a great question. So the slider in Windows is essentially a platform intent, right? What you and I as a users, let's say I'm on the flight, I'm going to go back tonight, and if I have a lesser battery life, I'll probably move to the best power efficiency because I want it to last for the duration of my flight. Right? But the thing that happens is when that slider is set, that gets communicated to us via existing interfaces that we have built with operating systems such as hardware P and other things that we get, and also OEMs set things like PL limit. So for example, let's say I have an OEM X laptop and they say that, oh, you moved to cool and quiet mode, let me reduce your PL limit. That gets communicated to us also, right? So then we kind of use that information and say that, hey, now, does my performance and efficient core ordering change? Because I have lesser power to CPU, and if, let's say, NPU is running something and my power to CPU goes down even further, are E-core is now most performant? And that's how we communicate that back to operating system saying that, hey, there is change because user selection changed from top or OEM selection changed.
That's really cool. I had no idea that it worked that way. That's fascinating. Okay, we're talking about laptops, so we're talking about Panther Lake. So we're talking about CPUs with integrated GPUs, and he specifically cited an example of a game that needs 8 threads and you're using 8 E cores rather than the P cores because you'd rather have the TDP go to the on-die GPU on
Absolutely,
chip GPU.
Yeah.
And how does that, is that an OS decision, or is that just is the thread director aware of what's going on the GPU side of the SoC, or is this more of a, hey, the TDP for the chip has gone up and we know that there's less thermal or less energy overhead? Yeah,
so thread director directly is not aware of what's going on the GPU side, but indirectly it is aware of that by knowing that, hey, my budget to core reduced, right? If other IP is taking power budgets such as GPU or NPU, all thread director knows is the core budget has reduced, right? But then what we do in this case, what Tap talked about was, there is an optimization in our graphics driver, which is our new intelligent bias control, IBC as we call it. IBC provides some telemetry to the platform software and power management saying that, hey, I'm GPU bound now. Right? When we see that telemetry, then we combine what's the efficient core from thread director feedback along with the OS PPM scheduling policy saying that I want to use efficient cores first. Why? Because I'm mostly GPU bound, right? And that provides me more headroom for graphics.
So this means when I'm benchmarking this stuff early next year, I'm going to have to run some benchmarks at balance and some benchmarks at performance and some benchmarks at...
Oh, the good part about this is this even runs in this particular optimization that we talked about. It even runs in best performance mode.
Oh, okay. So it knows...
you are going to get the benefit of it no matter what.
I think that's one of the neat things that I don't think I really appreciated is that you don't need an Intel chipset driver. I mean, you need the Intel chipset driver, obviously, but you don't need some special software running
Absolutely.
on the host that says, hey, here's what we're doing.
Yeah, I mean, there is the platform software stack is already enabled. We have our graphics driver goodness already running. We have our power management already running. The PPM hooks that Microsoft provides are all public. So we use existing infrastructure to come up with new optimizations on top.
That's really cool. So, okay, so then we talked about Windows a little bit. How's Linux doing on the same front?
Yeah, so Linux, uses part of thread directory information. Like they use class 3 quite a bit to figure out what is non-scalable work, if there is spinning happening, etc. There are in process of upstreaming more and more changes from Intel side. I mean, Linux, basically the way we have to go is, we don't control all the upstreaming. We propose the changes and then it goes through reviews and things. So that's what is happening. The Linux community, as I see, at least at Intel, talking to them, they are excited about new changes that are coming in. They want to take advantage of it. So we are looking forward to, making more progress there.
So one of the things you talked about a little bit yesterday in your talk is the performance, when it's the right time to move a thread from one CPU core to another, from one type of core to another. Like I don't know if people have a good sense of what the performance penalty is for that and what the impact of doing things like that is.
That's a great question. So typically, even though we have hybrid architecture, the cost of moving a thread from one core to another is just a cost of context switch plus the data that we have to move, right?
Okay.
So when we move a thread, there's no direct cache to cache. So we go through LLC, right? We write all the data and we bring it back up to another core. That's same as what you have on homogeneous as well, right?
Okay.
Typically, I mean, I'm just quoting a number approximately, like we expect around 100,000 cycles for that.
Okay.
And again, that's nothing specific to hybrid. It's just a cost to move a thread.
Okay.
Now, there is also C-state and other things involved in here if the thread core was in deeper sleep states and wake-up cost, and that depends on architecture to architecture, but that's what we have. And that's why, if you look at it from operating system side, sometimes they don't move the thread right away because if the thread is short running, let's say it's going to finish in 50 microseconds, right?
Okay.
We do have that. I mean, we have some threads that are extremely short. They may not move the thread right away. Why? Because the cost to move might be more than what it would have taken to finish that thread.
Right, so 100,000 cycles, we're talking about microseconds, not milliseconds, right?
It's just CPU cycles, the clocks, yeah. So it's in microsecond level. It's nothing in millisecond. Millisecond is like forever for CPUs.
Okay. Time gets weird when you're talking about CPUs, and I know you're used to thinking about this, but I know I'm not. I don't think folks at home are. I guess the next step is, how does does this work the same on desktop when you're not thermally limited by the structure of, obviously Panther Lake's not a desktop processor, but.
Absolutely, yeah. So in our previous generation, which is Alder Lake, Raptor Lake, Arrow Lake, we have had thread directors in there, right? Mm-hmm. It uses, conceptually it's the same thing. Same interfaces, same information that gets produced. Now the thing that will happen on desktop, as you rightly said, right? We are not thermally limited, people don't change PL limit to lower value, there is no cool and quiet mode and things.
Yeah.
The budget to CPU is going to be less constrained in that case, right? So there are less chances that the ordering of the core changes, such as, there will be less chances where E-cores are going to be more performant or anything. And but other than that, the functionality and information that goes to operating system on classification, everything is the same.
Fantastic. Thank you so much. There's going to be more awesome videos on the Full Nerd channel right down here. Please subscribe and click on that one. It's good.